right, everyone. So I just want to show you, first of all, I'm really happy the class did really well on this exam. And you either have a version that has stats in the header in small letters or in capital letters. And the keys are up here. So I'm not going, there's just one question that I'm going to go over because most people did so well that, and things are marked wrong or right on your exams. Does anybody want me to go over all the questions? No, okay. I was just some people asked me to just go over one question, which I can quickly do. Let's go to the document camera. Now that you know where the keys are, let's just go to the document camera and I zoom in here. This is where we left off, but quickly I can go over. First off, if you have a 0 here, that means you didn't get any points taken off. So which version is this? This is I think it was the same on both versions for this question that people want me to go over. It's this one right here. I think this one's the same on both versions. Let me just check. Yeah. Okay, so it's including the outlier. If you include the outlier, why does it make it go stronger? Because without it, it would be almost no correlation. You include it, and do you see how you get this stronger correlation? You'll get a positive correlation. Here, you'd get almost 0. Now, if you include the outlier, look, without the outlier, you have a pretty strong correlation. Now, when you include it, it weakens it. Without the outlier, you have a pretty strong negative correlation. Now it weakens it. They're all the same way here. It weakens the correlation when you include it, because you're included. It's going to weaken it. It's far away. So that's the only one that some people had questions. Anything else you want me to quickly go over? Mostly everybody got, how about if I try to let you out a little bit early, so that you can ask questions on your own. If it's misadded, you can tell me. If you really don't understand why you got something wrong, we wrote the right answers on there, the keys up online. If you really don't understand why you got something wrong, just come to office hours. Okay, now, where'd we leave off? We left off here on page 166, right here. And let's look at this. A gambler plays roulette. I'm sorry, with carrying all the exams and everything, I didn't get a chance to bring the roulette wheel again. But I know, I'm sorry. I'll bring it again next time, so I didn't get a chance to bring it. It's too much to carry. But you remember what it looks like. Now, let's look at this example here. A gambler plays roulette 150 times, staking $1 on the number 10 each time. Now, let's look at this. Do you remember? I hope you remember there were 38 numbers. It's 0, 00, and then 1 through 36. So there were 38 slots on the roulette wheel. And when it says that he's staking $1 on the number 10 each time, what can happen? He can either win $1, and it says that the bet pays 35 to 1. So that means for each dollar, he can either win places $1. He can either win $35 or lose $1, loses $1. It pays 35 to 1. So if you can win 35 times more than what you place. If you place $2, he'd win 70 or lose $2. All right, now, first of all, let's make the box for a single play. So we're going to just translate it into a box model and just think about one play. All right, instead of the 150, that's N. Let's just think about one play. For any of these roulette games, there's just two things that can happen. You can either win or lose on a single play. You can either win or you can lose. If you win, how many dollars do you win? If you lose your dollar. We'll call that negative. If you win, how many dollars do you win? 35. You could put dollar signs, but we don't need to. Okay, now, how many ways are there to win? One. How? If it lands on that number 10, there's only 1 out of 38 ways to win. How many ways are there to lose? 37. Why? Because there's 37 other numbers. So there's always 38 tickets in the box representing the 38 slots that the ball could fall into. Hey, that doesn't look good. It's so, why is it looking that way? So dark up there. Why? Is that coming out okay on the camera? Okay, I'm sorry, it looks so dark. Okay, so 38 tickets. Now, so what are they asking us? What's the expected value and the standard error of the gambler's winnings? So what we want to know is if he played 150 times, what would he expect? Well, it's a chance process. So, it's going to vary, but what would you expect? First of all, would you expect him to win or lose? Lose, because there's more ways to lose than to win. Let's look at the average of the box, and you'll see. If the average of the box is negative, then you can expect him to lose. So let's see what the average of the box is. So let's calculate that, the average of the box. And what do we have? We have one ticket that's $35. And then how many do we have? 37 tickets that are losing money, losing -1. So the numerator is what? This is all in dollars, by the way. I should put the dollars there. Okay, so what's that add? 35 minus 37 is what? Minus $2. Okay, but is that an average? No, that's a sum. We want the average, so what should I divide by? How many tickets are in the box? 38. So that is the average of the box, and it's negative. And if we divide that, it's about negative a nickel. It's negative. This would be negative a nickel right there. But I could do it a little bit more exactly, because I think I might ask you on your homework, so it's a little more than a nickel loss. So that's the average of the box. Now, on any one play, could he lose that? No. On any one play, he can only lose $1. Right? Because he bets $1 and either loses that $1, these are dollars, or else he wins $35. There's nothing else that can happen on a single play, and I'm so sorry I forgot my roulette wheel. Would have been fun to play it. Oh well. So this average of the box is not necessarily something that has to happen, just like the average number of children in the US is like 2.2, but nobody has that number of children, right? So the average is not ever going to happen. It's always going to be, on any one play, he'll lose $1, or if he gets really lucky, he'll win 35. But so now the question is, if he plays it 150 times, what would you expect him to get? So the expected value for the sum of 150 draws from this box is going to be what? Do you know what the expected, you remember what the expected value is in general? It's n times the average of the box. So it would be what? I'll just write that, n times the average, just so you remember. So in this case, what's n? It's 150 times this amount right here, which is, in dollars, -0.0526, And what do we get? We get that we expect him to lose what? $7.89. Okay. Now, even though that's the expected value, do you think that could ever really happen? Exactly $7.89? No, there's no change involved here. It's going to be dollar amounts. So that's impossible, but it's the expected value. It's just like an average for a chance process. Do you get it? But it could vary. It could vary quite a lot. And that's the thing you're interested in. What if you win a bunch of times? And so that's the standard error. That's the standard error. So let's look at that. So the standard error of the sum of 150 draws, it's going to be what? The square root of n. Remember we learned this last time? We talked about the square root law times the standard deviation of the box. So that's going to be the square root of 150 times the standard deviation of this box. Now, how are we going to do this standard deviation of this box? It's exactly like, we can use the shortcut method because we just have two types of tickets. Remember how we do it? We subtract, we look at the difference of the numbers written on the tickets times the square root of the proportion or the fraction of the box that has one of the tickets times the other. So let's do that. All right, so in this case, you look at the spread inside the box. The bigger that spread is, the more variation there's going to be, right? For the standard deviation, it's going to vary more. If you could just get -1 and 1, that makes a huge variation there because you get 35. So that part is going to be what? 36, the difference between those two. The absolute value of 35 minus -1. So that's 36. Now, times the square root of, now we have 38 tickets in the box. How many of them, what fraction of them have 35 on them? 1. What fraction of them have 37 on them? And have -1 on them? 37. Remember that this has to sum to 1. We're multiplying, but that has to sum to 1. All right. And when we do this, what do we get here? We get a 36 here, and here it turns out we get 0.16. And so together, we multiply these together, and we get $5.76 for the standard deviation. Whoa, I didn't leave very much room, did I? I am so sorry. This is what's going to go right inside there. So the standard error of the sum is equal to what? The square root of what's n? How many times are we? 150 times this number right here. That's the standard deviation. So times that, which is $5.76, negative, positive. Whoa. Can the standard deviation ever be negative? No. So it's times $5.76. And when we do that, where can I put it? Right there. I got $70.58. So that's right there. Let's rewrite this somewhere where it makes sense. What are we even talking about? What are we even talking about? No, really. So I'm just gonna, I just need a piece. You have some questions on that? What? Yeah, I don't blame you for not understanding. So that's what I was going to say. Listen, what are we talking about here? So I just wanted to get a piece of paper so I could show you. Hold on. All right. So what are we talking about here? First of of all, I'll explain it to you. And since I don't have my roulette wheel, maybe we can play it online somewhere. Okay, so first off, look at this. So pretend you're at this casino, and pretend you're playing this bet 150 times, or there's 150 different people each betting on a single number, right? On this one single number, right here. Now, so you want to know, I'm just going to write it again. You want to know what the expected value of the sum of your draws is. And we did n times the average of the box. And when we did this, you know, all the calculations are here. We ended up, I'm just going to simplify it, we ended up getting this number. Almost $8. So you expect to lose $8, but is that going to happen every single time? No, it wouldn't be gambling if that's what happened. The whole fun of it is that there's variation. You could win a whole lot. What if you it landed on number 10 a bunch of times? You could also lose a lot, which makes it kind of risky and fun for people, right? So for some people. So that's what the standard error tells you. Yeah, you'd expect this, but how much is it going to vary? What if I do this? Do I really want to, $8 isn't very much. I could, losing $8 might not bother me that much. But what if I was going to lose a whole bunch? Like, what if there's a good chance I could lose $100? Then I might not want to play it, right? So that's what the standard error tells you, how much variation there is. So the standard error for the sum we saw, we worked this out last time, but now we're just looking at the formula. We did that, and what did it come out to be? $70. Whoa. So now you might think, do I really want to play this game? In other words, we'd expect to lose $7.89, about $8, think of it, about $8, give or take about $70, 71, give or take about. Sometimes it makes it more confusing to work these things out so exactly, because we're not talking about an exact thing. We're saying give or take about $70, but I'll write it the way we did it. And later we're going to see that in the next chapter, we're going to work out the probabilities. This give or take number is going to, if we play enough times, it's going to be like one standard deviation, one standard error. So it'll be, if it follows the normal curve, that would be about 68% of the time. And then about 95% of the time, we'd be within two of these. So about $141 in either direction. So we could lose quite a lot, almost $150 within that, or we could win pretty much too. This is a risky game. This is fun because you can win or lose. Let's see. Hold on, let's see if we can play it. So let's go to the PC. And let's see, if we go to our data program, what am I on? Am I on Internet Explorer? No. I have to get to Internet Explorer probably to do this. Just because it's a Java applet and it won't work on Firefox. So is this Internet Explorer? I never go on Internet Explorer. I don't even know what it looks like. Okay, so now we do, so where do you do the search bar? Right here? Where is the search bar? And stick it in. I just want to, just Google something. So what do you do in Internet Explorer? Come up here, somebody help me out. Do I just open a new window? Oh, here it is. Wait a minute, this is good. Stat 100 computer program is very active. Let's try it. We're here. Okay, so now, it's so small. So how do we make it look bigger? Is there a little thing here? A view bar? Oh. All right. Anyway, I'll go to these box models and see what it looks like. Hopefully it will be bigger so you can see it. And now we wait for a Java applet to come up. Does anybody know how to make this screen bigger, like Control Z or something? Control what? No, that gets rid of it. Control Shift Plus? Will that make it bigger? Yeah, that does a good job. Okay, so now let's pretend, let's make our box, okay? So what was in the box? We had one what? 35? I'm going back to our box. Either win 35, or how many ways were there to lose money? There was 37 ways we could have lost what, $1? All right, so there's our box, and we'll accept the box. Look at all the ways there are to lose. Hey, look at this. Can you even read that? This says the average of the box is negative 0.05263. Does that look familiar? Look at your average of the box. And the standard deviation is $5.76. Actually, more exact. Okay, so we got all that. And now what do we want to do? We want to draw from the box. So, here's our game. Let's play it. You want to do it 150 times and see what happens? Is it going to be with replacement or without? With. All right, let's see what happens. All right, so let's watch. We'll play it. We'll start 100 times. Did we get any 35s yet? No, look up here. We must have. This is how much we're winning. We're losing. Come on. Losing. This is our net gain so far. So we lost. Oh, we're going to do 50 more times. Okay, so let's do 25. Losing. Ugh. Keep losing. We have 25 more. Ah. So, what happened here? Here's what happened to us. You can look. You can see how many times we won. We must have won sometimes. On the 12th time we won. We won one time. Did we win any others? Yep, there was another one. Oh, look at all those losses. Anyway, so we just figured out that we would expect what? We would expect to lose how much? We just figured it out. What's in your notes? $7, right? But that's right here. That's what we would have expected. Negative $7.89. It's much more exact here. That's what we expected, but we said give or take what? Give or take a standard error of 70.57. Isn't that what we said? Well, our error was just right within that range. The error that we got was $70 less. We ended up losing $78. Does that help explain it to you over here? Does that help? See what we're doing? What? Does that help everybody understand what we're doing or not? Not really. You want to play again? We'll play again. Okay, let's start over. All right, so let's say we were real gamblers here. Okay, so we're going to play again. Now, this tells how many tickets are in the box. This is our average. You want to go really slow? I can show you if we went really slow and just play 10 times, what happens. Watch. We lost. We lost again. $2 so far. Woo, we won. $33. Lost. Oh, we're doing good with only. Lost. We should quit right now, but we're going to lose a few more times. We're only playing 10 times. I should show you the whole screen so you can see the 10. So you can see how many times we're on our 10th time. We won $26. Now do you see? Is it helpful if you see it slower? All right. Now if we wanted to figure this out mathematically, this is an easy one because it was only 10 times. So 10 times the average of the box The average of the box is negative a nickel. Multiply that by 10 and you get negative 50 cents, basically. So we'd expect to lose 50 cents. But there's a big variation. If you do the square root of 10 times the standard deviation of the box, you get this right here, right? Square root of 10 is about 3. Standard deviation of the box is a little over 3. Yeah, so you get about $18, give or take 18. But we got lucky. You'd expect to lose 50 cents, give or take about 18, but we gained $26.50. Now our error, so we did well. Do you understand a little bit better now? When we went slow? Now this is what gamblers do. I'm doing good, so let me keep going. It's my lucky day. So you keep playing and watch what happens. Now we'll go fast. Or do you like it slow? I think you understand it. Let's go fast. How many times? Let's say we play another 10 times. What happens to our money? Going down. Oh, let's do another 10 times. Oh, come on. Oh, shoot. Now I've got to win back my money. See what happens? Oh, I'm down. I was up 26. Come on. All I need is, I'm not going to lose here with nothing. I have $100. Come on. Oh, now I got to do it. Oh, see? I won. Just a little more. How many times have I played? Oh, over 100. That's what happened. So I've lost $38. What did I expect to lose? I expected to lose what? 5. Didn't do very well. I kept losing. So that's the idea. And if you want to see what happens in the long run, change to batch, and let's do 1,000. And you're going to see it really fast. There's all the 1,000 plays. Whoa, not very bad. We actually ended up gaining. Let's do another 1,000. Sorry. Don't get addicted to this stuff. We should lose more. Oh, we've won. You see, it's a chance game. Look at this. Let's quit while we're ahead. We've got $130. Time to quit? Yes. Okay, good. Thanks, lucky class. All right, let's go back to the overhead. So I hope you understand it better now, and let's turn the page. Now, all right, so we're going to do the same thing with a much less fun example. A multiple choice test has 25 questions. Each question has 5 choices. What if you guess at random on all? What's the expected value and the standard error? What do you think? Let's see. Well, first of all, you make the box for a single play, right? Don't you want to do that? Make it for a single play. And a single play, what can happen? There's 5 tickets, 1, 2, 3, 4, and 5. And what can happen? You can either win, get it correct, or you cannot get it correct. And we're just counting up the number of correct answers, right? And what's n? How many draws are there? 25 right there. So n is going to be 25 draws. And of course it's with replacement, because every question is going to look like this. If I took out 1 and didn't replace it, it would mean on the other 24 questions, if I got it correct here, you wouldn't be able to get anything right. All right, so now let's figure out the average of the box, because we're going to need that for the expected value. So what do? Just add up all the tickets in the box, and it's 1 plus 4 zeros, which is 1 over 5. So the average of the box is 1/5. And what is the standard deviation of the box? We're going to need that too. Let's do that for the standard error. So what's the standard deviation of the box? Do you remember? Well, you take the number that's the bigger minus the smaller, the absolute value of that, well, in this case, it's just 1 minus 0, times the square root of the fraction of the tickets. How many tickets are there? 5. So 1 out of 5 times 4 out of 5. We can do this one in our head. That's 1 times the square root of, what's 1/5? 0.2? And what's 4/5? 0.8. And what's the square root of 2 times 8 is 16. You know the square root of 16 is what? 4. Now 0.2 times 0.8 is 0.16. So that would be the square root of 0.16. The square root of 0.16 is just going to be 0.4. 0.4 times 0.4 is 0.16. By the way, this will help. If you just have a box that has ones and zeros, in a 1-0 box, what is the biggest the standard deviation could ever be? And what's the smallest? You think it's 1? I don't think that could be. Okay, let's try. Let's start with, what if you had a box that was a 50-50 split? 50-50, right? So the standard deviation is going to be 1 minus 0. Can we just forget about the 1 minus 0 because it's always going to be 1? I mean, if you want to put it in, you can. But it's going to be the square root of 0.5 times 0.5, which is the square root of 25, which is what? What do you think that is? 0.5. Okay, let's try another one. What if we did, let's just do ones we know. So let's say we have a box that has the one we just did. We don't have to write it down. Let's say it has a point, what? What did we just do? What did we just do? 0.2 times 0.8. And we said that's the square root of this, and that's 0.4. Let's do another one. How about 0.1 times 0.9, 90%? What do you think that's going to be? What do you think that's going to be? What's the square root of 9? 0.3. Do you think you can ever get higher than 50%? Look how it's going to go. What if I went all the way down to all ones? All ones are I'd have 1 times 0. If it was all ones or all zeros, what's that? That's 0. What did I do here? Look what I did. I did this all wrong. 0.1 times 0.9 is point what? 0.09. Sorry, no wonder. That's 0.09, which is equal to 0.3. I am so sorry. Do you see how it goes? So the standard deviation of a 0-1 box has to be between 0 and a half. Look, if it's ones and zeros like this, just half and half, the average is a half. This has a standard deviation. This deviates by a half down. This deviates by a half up. That's the biggest it can be. The most uncertainty. When you have 50-50, you don't know what you're going to get. 50% 1, 50. If you have all ones and no zeros, you know for sure you're going to get a 1. So anyway, so let's just go on. That was an aside route. So this was 0.4. All right, now the expected value of the sum, that's what they're asking for, is what? N times the average of the box, and N is what? Where is our N? 25. So it's going to be 25 times 1/5, which is what? We'd expect only 5 right. 1 out of 5. You don't really need statistics for this. 1 out of 5 times you expect to get a right answer. So if there's 25 questions, you'd expect to get 1 out of 5 of 20. 1 out of 5 of 25, 1/5 of 25 is 5. But this one is anti-intuitive. This is not intuitive. And that's the square root of N times the standard deviation of the box. So that's going to be the square root of what? 25 times 0.4. So that's 5 times 0.4, which is 2, right? So you'd expect to get, you wouldn't do very well on this test. You'd expect what? To get only 5 right. Only 5 correct. But it's a guessing game, so it's give or take what? 2. In other words, what do I mean? Between 5 minus 2, between 3 and 8. And I did that wrong, 3 and 7. 5 plus 2, 7, 5 minus 2, 3. Any questions on that? I'm so happy you stopped me. If you don't really know what's going on intuitively at all, or don't know what I'm talking about, please say, I don't know what you're talking about. Because why go on and learn stuff if you don't even know what I'm talking about, right? Okay, so now here's our summary, just these that you should remember. And on and upwards to the next chapter, where we're going to look at the expected value and the standard error of a different statistic, not the sum of the draws, but the average and the percent. So let's look at the next chapter. All right. So, first off, before I start, any questions? Any questions at all? All right. Now, in gambling games, you're interested in your net gain or loss, in your winnings. Same when you're, for a lot of, So we're interested in the statistic of interest was the sum. But there's going to be a lot of times where you're not interested in the sum. You're interested in the average or the percent. So let's look at how you would figure out the expected value of an average. All right. So the expected value of the average is equal to the average of the box. You don't need any formula at all. It's just common sense. For example, let's just write it up, what I said. The expected value for the average of, I don't care how many draws you have from the box, it's just going to be the average of the box. For example, let's look at this box right here. 100 draws are made at random with a box containing these tickets. And what's the average of this box? If you add them all up, what is it? 8 plus 8 is 16 plus 4 is 20 divided by 5 is 4. So the average of this box is 4. All right? Now, if you drew, I don't care how many times you drew from the box, let's say you draw 5 times, wouldn't you expect the average wouldn't you expect to get, it would be each one of these is equally likely, so you'd expect to get each one of these, they're equally likely, and you'd expect the average to be adding those all up divided by 5, which is 4. If you drew from this box 10 times, wouldn't you expect to get, since they're all equally likely, your best expectation would be to get 2 of each? Okay, so you'd get 2 of each, and then you'd divide by 10, and you'd get the average of the, what else would you expect? You wouldn't expect, think about it this way, you wouldn't expect to get anything higher. Would you expect to get all 7s? If you drew from here 100 times, would you expect to get all 7s or all 1s? No, you'd expect to get, your best guess is to get about the average. So the average of all your draws is just going, there's nothing to figure out here. Your expected value for the average is whatever you have in the box, the average of the box. Does that make sense to you? Why would you expect to get higher than the average? Why would you expect to get lower than the average? You will, because it's a chance process, but would that be your expected value? Would it? No, why would it? It's not common sense. So there's no formula. It's just really easy. And for the sum, we said n times the average of the box. Here is okay, so what is the expected value of the average of 100 draws? the expected value of any average, I don't care, the average of 20 million draws, is just going to be the average of the box. So in this case, it's 4. You'd expect the average of the draws to be the same as the average of the box. But of course, it's going to vary. This is a chance process. So the typical variation around the average is called the standard error of the average. And here's our formula for it. It's the standard deviation. It's very, very similar to the one for the sum, except you divide by the square root of n. Because with an average, you divide. You know, how do you take an average? You sum things up and you divide by n. With a sum, the more times you draw, the bigger the sum gets. Okay, so the bigger your error would get as well. So here's why. Let's go back to I can show you how it's connected. Let's go back to the square root law. What did the square root law say? The square root law we've been doing says the standard error of the sum of n draws varies according to 2 things. The more variability in the box, the more error you have. We saw that. When there's a 35 and a -1 in the box, instead of just a 1 and a -1, there's more variability. It's a riskier game. You can win more and you can lose more. So it depends on that, the standard deviation of the box, and it depends on how many times you draw. The more times you draw, the more your error could be, the more you could get something, the more error you have. You know, because each time you draw, there's more error. But it doesn't scale as n, it scales as the square root of n. That's what we did. Now we're interested in the average. So to change from a sum to an average, you always divide by n. So just divide both sides. Watch. Okay, so this is what we have so far. Standard error of the sum of the draws is equal to that, right? Now, what if we divide both sides by n? Here, all I'm saying is, how do you get an average? You sum things up and you divide by n. So now we have the standard error of the average is just going to be divide by n. That's how you always get an average. You sum things up and divide by n. So let's divide both sides by n. That's all we've done. We're deriving this. I just want to show you how we get this. It's very, very easy. So here's for sum, for average, you divide by n. And now let's just simplify that. If we simplify this, how can you simplify it? Let's keep the numerator the same. And what are we going to do to simplify? We'll change n to the square root of n times the square root of n. Like if that was 25, I'm changing it to 5 times 5. And then these cancel, and there it is, our formula. So that's it. So basically it's the same, you know, an average, think about it, a sum is bigger, sum. So you multiply by the square root of n. With an average, you're dividing, so you divide by the square root of n. It's not very hard to remember. So for example, 100 draws are made at random with replacement from a box containing these tickets. There we go. You'd expect the average, let's write what the average of these are. The average is equal to 4. Okay? So what would you expect the average, oh, I should tell you what the standard deviation is too. What is the standard deviation here? Should we have, can I just tell you because we're running out of time? Or do you want me to work it out? You'd have to work it out the long way. You'd subtract 4 from each one. We can do it. It won't take us long. To get the standard deviation, what would we do? We'd subtract 1 minus 4. That's a negative 3. 3 minus 4. That's a negative 1. 4 minus 4. What's that? 0. 5 minus 4. What's that? 1. And what's 7? What's our last deviation? Hello? 3. There's our deviations. Do they sum to 0? Yes. Now, since they sum to 0, we have to square them. So we square each one. And then what are we going to do? What are we going to do after we square them and add them together? what are we going to do next? First, we have to take the average of them, right? You have to take the average of the squares. It's the root mean square of the deviations. So you take the average, there's 1, 2, 3, 4, 5. And then we're going to square root them. Okay, so what do we get? 9 and 9 is 18. 19, 20 divided by 5 is 4. So we have the square root of 4, which is 2. Okay, so let's write our standard deviation is 2. And that looks about right. Because here's a deviation of 1 and here's 3. So about 2 looks right. All right, now let's do an iClicker question. Let's just do this as an iClicker so I can give you some points for coming here. And so you'd expect the average to be what? Give or take about what? This is what you're going to be using, this formula. So let's see if you can do this. So I want to start the slideshow. Where do I go? Oh, it's this little thing. Is this open right here? Yeah, you are. Is this the one that opens it up big? There you go. Yeah, use your iClickers. This is not hard. What's the average of the box? What's the average of the box? Even if so what would you expect the average of any amount of draws to be? Would you expect it to be any higher or lower? This is a no-brainer if you know what the average of the box is. Why would you expect it to be higher or lower? I mean, you wouldn't expect to get all 7s, or you expect on the average to get the average. So this one you should all get. There's no reason to expect the average to be higher or lower. All right, y'all done here? So let's stop it and look and see what you got. Okay, the average of the box is 4, so you'd expect you're doing the expected value of the sum here. People who answered 400 are thinking n times the average of the box. That's if we summed them all up. That's not what we're doing. We're just wanted the expected value of the average, not the sum. That's why it's not 400. Okay, so let's go to the next one. Okay, sorry. Let's go to the next one. Now, we already did this one. You'd expect the average of the 100 draws to be 4. Well, I just gave it away. That's 4. Now let's do this one. Give or take what? I'm going to start it. So now you want the standard error of the average. The SD is 2. The question is, are you going to multiply by the square root of n or divide by the square root of n? There's your n, 100. The standard error of the sum, you multiply by the square root of n. The standard error for the average, what do? Divide. The standard deviation is always going to be in the numerator. Just the question is whether you multiply or divide by the square root of n. You have an average. You don't have a sum here, so what are you going to do? Multiply or divide by the square root of n? What's the square root of that? So you're going to take your standard deviation and move it over how many decimal places? Because you're dividing by what? Okay. Should we stop? Anybody still need time? No. So let's stop it. Yes, we divided 2 by the square root of 100. 2 divided by 10 is 0.2. That's all we did. SD divided by the square root of n. 2 divided by 10. All right, let's go back to the document camera. And I think you know how to do this. Let's write it in here. So you'd expect the average to be 4, give or take about 0.2. Why? This is the expected value of the average, which is just the average of the box. Let's just write it down so when you look at your notes later, you'll remember. So the average of the box, which is equal to 4. That's how you got that. Now, how did you get this? You got this by saying the standard error of the average is SD divided by the square root of n. It's this right here. Which is 2 divided by, there's your n. 2 divided by the square root of 100, which is 2/10. That's how you got that. Any questions? All right, so let's turn the page. Okay, we're going to do the same thing with the next one. Maybe we should do it as an eye clicker just to give you practice. All right? Raise your hand. You want it as an eye clicker? Raise your hand. Do you want to do an eye clicker? Do you want it as an eye clicker? Raise your hand if you want it as an eye clicker. I'm just curious. Raise your hand if you don't. Wow, that was too hard to tell. How about we do an eye clicker? We'll do an eye clicker. And I'll ask you the question. Do you want it? No. All right, we're going to do an eye clicker. Okay, because I think you're thinking about it more. Okay, so I'll give you the average. Do we have to go through the standard deviation again? Okay, so let's say the average is easy. 12 divided by what? 4, so the average is 3. And the standard deviation is also 3, right? Yeah, it's also 3. Now, this one we'll do together, then we'll do this one separately. I mean, on the eye clicker. This one we're going to do is together. Okay, just because you might have forgotten. You'd expect the sum of the 36 straws. The expected value of the sum is what? You're going to add up. It depends on if you just drew once or twice, the more you draw, the sum is going to grow, right? So it's going to be n times the average of the box. So what would you expect it to be? 36 times what? Hello? 3, which is 108. That's what you're going to put here. And the standard error of the sum, because you're summing things up. Every time you do it, you're adding a little more error. It's the square root of n times the standard deviation of the box. So that's the square root of 36 times what? 3. So that's 6 times 3, 18. Now, how is this one going to be different? This is, you'd expect the average of this 36 straws to be what? And give or take the standard error. What you're going to put in here is just the standard error of the average. And this one's just a no-brainer, the expected value of the average. Okay, so let's do it. So let's go back to the PC and get rid of this and go down to the next one. Okay, here it is. Let's start it. And we're going to do this first. Fill in this blank. You'd expect the average of the draws. This is no formula. What's the average of the box? Why would you expect it to be any higher or lower than that? And this is going to be the next one, so think about this one after we finished. This is going to fill in the standard error blank. Okay, can I stop it? All right, so this is just going to be 3, right? Good, you all got it. It's just the average of the box. Now we're doing the next one. How come it didn't start? Come on, there it goes. What happened? What? What? What did I do wrong?
Okay. Click it once and let it think.
Let it think. Why should it have to think? We're doing thinking all the time. We're the ones who are supposed to be thinking.
But if you click it twice, then it starts and stops.
Okay, so now you think it's going to go. I'm just getting impatient. I hate to waste time. I hate to waste your time. It's taken an awful long time to think. Okay, do you think I should give it one more chance or just go?
Click it again.
Click it again and then wait. There. Thank you, guys. All right, so we're answering this one. We're going to go the whole time this time because we have to, the homework's posted and it covers this whole chapter. So this is going to be our last eye clicker, and then we're going to go through the rest of the notes. All right, everybody done here? And what is our answer? It's going to be, let's look at it. Stop. And what did you say? It's SD divided by 6. So it should be 0.5. Great. You got it. Okay. So that was, let's just continue here, because this is the next question. Now suppose you draw at random with replacement from the same box, but this time you're only interested in counting 2s. Change the box to a 0, 1 box. Which box is it going to be? If we change, you're only interested in counting 2s. So if you get a 2, you count it as what? I'm going to start this up. If you get a 2, you count it as what? You're counting 2s. You get a 2, you count it as 1, 2. What if you get anything else? What are you going to count it as? You're only interested in counting 2s, so we're going to change this box. Which box is it? What do we count by? 1s and 0s, right? You count by 1s. Hey, I got 1 this, I got 1 that, I got 1, 2. And if you don't get a 2, what do you count it as? It's pretty easy. All right? So which box is it? All right? So now we're going to stop it. Anybody have more time? Need more time? Okay. All right, so let's stop it. And which box is it? Yeah. Oh, wait a minute. Did you get it right? Yeah. I can't remember what they were. Yeah. Okay, so let's see, you got it right. So let's go back to the document camera. We did our first question here. Okay. We changed it to 0, 1, 1, 0. And now, when counting anything, make a 0, 1 box. Come on. All right? So now, what are they asking for? What's the expected value of the number of 2s in 36 draws? So, the expected value of the number, that's the same thing as the expected value of the sum. You know, you're counting up. All right? Which is n times the average. Of this box, the average of that box is what? 2 over 4, which is a half. Half the box is 2s, so you'd expect half your draws to be 2s. So it's what? 36 times a half. So you'd expect, this is pretty common sense, you'd expect out of 36 draws to get 18. But what about the standard error of the number? You're not going to get exactly 18. So what is it? It's the square root of n times the standard deviation of the box. So that's the square root of 36. Hey, can you just figure out in your head what the standard deviation of that box is? Half 1s, half 0s? Remember we talked about it? What's the biggest it can be? Half, yes. The standard deviation of this box is equal to the square root of 0.5 times 0.5, which is a half. All right, so it's times a half. So we get 6 times a half, and we get 3. If you wanted to do it the other way, the standard deviation of the box, I did it so quickly, and I apologize. The box looks like this. So you could do it like this. You could think, 1 minus 0, which really doesn't matter, times the square root of 2 over 4. There's 4 tickets total, and that's the same thing as the square root of 0.5 times 0.5, which is equal to 0.5. Okay, so you'd expect 18 twos, just to tell us what we're doing. You'd expect 18 twos, give or take what? Give or take how many? Give or take how many? 3, thank you. All right, now, so we're going to do now this, when you change to a 0, 1 box, you have percents. What's the percent? That's what we're going to do next, the expected value of the percent. All right, so it's the same thing. It's exactly the same thing. All right, now we're doing the expected value of the percent. All right, what percent would you expect? So you change to a 0, 1 box, and the expected value of the percent. If 50% of the box, 50% of box is 2s. So what did value of the percent of 2s in 36 draws is what? What would you expect? If 50% of your box is 2s, wouldn't you expect 50% of no matter how many draws? Yeah, what else would you expect? Would you expect 100%? It's exactly the same. A percent is just an average with a 0, 1 box. So you'd expect it to be 50%. There's no formula, okay? Where do I say this? I thought, okay, the expect right here. There's no formula because it's just common sense. It's the percent of 1s in that box or the percent of the, All right, now the standard error for the percent is just going to be like an average. But it's an average of a 0, 1 box. So you're using that box. So it's the standard deviation over the square root of n. Leave a space here. I want to show you what happens. So what's the standard deviation of this box? We already said it was what? We already said it was what? 0.5. The average is 0.5 and the standard deviation is 0.5. Okay, so you have 0.5 over the square root of what? How many draws do we have? 36. So this gives you 0.5 over 36 is 0.5 over 6. But this is not going to be a percent. Do you know what this is going to be? A decimal. We're going to have to change it into a percent. So to change it into a percent, like if you want to change 0.5 into a percent, what is it? 50%. If you want to change 0.75 into a percent, what do? Move the decimal place 75%. So that's the same thing we have to do here. So you just have to change this into a percent because right here you've got a decimal. That's just to change to a percent. So we'll multiply it by 100, or people are going to say, oh, multiply by 100%, you're not changing anything. This is to remind you that to change it to a percent. Okay? And then instead of getting this part is 0.083. This is what I'm doing. Times 100 to change it to a percent is 8.3%. Okay? And I just did that problem for you. I'm sorry, I squished them together. They were supposed to be separate. This one's supposed to be down here. So you'd expect, let's just say what we're doing, you'd expect 50%. You knew that before you came into this class. You'd expect 50% twos. Give or take, this is the hard part, 8.3%. That's all we're doing. Does that make sense to everybody? Okay, now, this last thing is, is just to show you the relationship between, look at this. The more times you draw, the bigger the standard error is for sums, because you multiply by the square root of n. But the smaller it is for averages and percents, because you divide by the square root of n, right? So this is basically the idea. So 4 times as many draws doesn't mean 4 times as much error. It means twice as much error for sums, but only half as much for averages or percents. So 100 times more draws means what? Square root of 100, which is equal to 10 times, means 10 times as much error for the sum, but only what for the average or percent? Only what? Not 10 times, but what? It's only going to be 1 over n, which is equal to 1 over 10 times as much. Let me walk you through this and you'll understand. So I'm going to walk you through this and you'll be able to get it, I hope. Okay, so let's turn the page and I'll walk you through it slowly. All right, so this is the idea. You flip a coin 2 times. Let's make the chances equally likely. The idea is this. You flip a coin 2 times, let's say, right? And you'd expect to get 1 head. What's the biggest your error could be as a number? You could be 1 off from that. You could get 2 heads or 0 heads. That's just 1 off. But percentage-wise, that would be a huge percent off. It would be 0%. You expect 50%, but you get 0%. Now, if you got 2 heads, you'd expect 1. But now, let's say you do it 2 million times. You flip it 2 million times. Well, you'd expect 1 million heads, but couldn't your error as a number, as a sum, be off? You could get 1,000,005, 1,000,010. As a number, your error is going to be off, but percentage-wise, you're going to get much closer to 50%. Do you think you'd really get 0% heads if you flipped it 2 million times? If you flip it twice, you could easily get 0% heads. So all I'm saying is that your error is going to grow as a number, but go down percentage-wise by the square root of n. So let's do these problems. In tossing a fair coin, fill in the blank to make the chances equally likely. All right, 2 plus or minus 1 heads in 4 tosses is about as equally likely as 18 plus or minus 1 in 36 tosses. So think about the number of tosses. Compare the number of tosses. 36 is what? 36 it's 9 times more than 4, right? 9 times more than 4. So when we're summing up, our error will be multiplied by the square root of 9, multiplied, which is equal to 3. So the error will increase, not by 9, but by 3. 1 times 3. But the percentage, let's look at that. 50% plus or minus 25% heads in 4 tosses is the same as 50% plus or minus what? It's going to go down. It's going to go down from 25, but down by how much? Down by what? Well, first you look at this relationship. 36 is 9 times more than 4. So the percentage of heads is will be divided, not by 9, but by what? 3. So it will decrease from 25% to 20 5% divided by 3, which is 8.3%. All right, let's see, they're not very hard to do. 10 plus or minus 2 heads in 20 tosses. Compare these two numbers, okay? How do they, this 20 times 100. So compare 20, this is 100 times more. 22,000 divided by 20 is 100 times more. 100 times more. So what do you think? 10 plus or minus 2 is going to be what? The square root of 100 is what? 10. So you're going to multiply 2 by what? 10. So you'll get 20 here. Right? 2 by 10. Oh, I should have looked at my directions. Sum or percent? It's sum. Multiply or divide? Multiply. It's by what? By square root of 100. I walked it, which is 10. So you say 2 times 10 equals 20. Sorry, I just did that in my head. I didn't see that I worked it out there. Okay, so let's do the other one. 2 is right here. How does your error change? First of all, it's going to go up. You're not going to put 2 in here because you have more tosses. So it's not going to be 2 times 100. It's going to be 2 times 10. Does that help? Now your next one. How does that going to change? 50% plus or minus 10%. You know it's not going to be 10% here. It's going to go up or down. It's percent, so it's going to go what? Is it going to go up or down? Down. So you say 2,000 divided by what? 20. So it's 100. So it's going to go down. Should it go down by 100? No, I want to take this 10% and I want to what? Multiply or divide? You tell me. Divide because it's percent. Do I want to divide it by 100? No, what do I want to divide it by? The square root of 100. So I get 1 here. Do you see it's 100 times more tosses. 100 times more tosses doesn't mean 100 times less error, it means 10 times. So is there any other ones? That's pretty much it. Okay, so here's all your formulas and the homework's due Wednesday.